You're good. Yeah. Any last drinks? Any last pizza? Do it now. Well, Aldi gets ready. I'm just going to do a little bit of an introduction. So we're part of the GDG Dublin team, and Carolina work here at Workday. Been here about 9 months now. You've seen Suhani, Aldan, who's an organizer and a speaker today, and Sylvia, she just joined us as a volunteer recently. So if you need anything or have any questions, please talk to any of us. Thank you, Workday, for having us today and for the pizza and the drinks, even with this awful weather. If anyone, we're hiring at the moment, so if anyone is interested, that will take you to the careers page. But feel free, there's a few Workday people here. Feel free to ask them for a referral or ask me. Can show this later. Or if you just go to Workday Careers, you'll see there are a few jobs. Awesome. So I'm also, for whoever doesn't know, I'm the co-organizer of Kodu. We run monthly events in case anyone's interested. It's more of like a web developer community, but we do a little bit of everything, and we do social events from time to time as well. So if anyone wants to join, we also have a content platform. So if you like to write articles or just share knowledge, it's a good place to go. Then next week on Tuesday, we have the React Spring meetup here in Workday as well. Same time as this one, but it will be focused on React. So that will take you to the meetup page if you want to join. And then another, Suhani is helping organizing a user group. It's a workshop in MongoDB, in case anyone is interested as well. It will be on May 29th, same 6 to 8:30 p.m. If you have any questions, feel free to ask Suhani. And then we have Aldan. He's going to be our speaker today. He works at Accenture as a technology research specialist at Accenture, as I said, at Accenture Labs. So yeah, he's going to do an adventure into Transformers with Aldi the Explorer, so you might know what's the topic here. So yeah, if Aldan's ready.
Sorry. Too early. Yeah. Okay. Here we go. We are ready. Yes. Let me just get prepared. I have a part of the outfit today. I hope you'll find it a little bit fun today, but I'm also gonna try to be a little bit technical at the same time. So let's see how this goes today. And now we are ready to embark ourselves on a journey into Transformers. Aldi the Explorer. Aldi. Aldi. We're gonna speak about many interesting things today. Transformers, attention, embeddings, a lot of interesting stuff. So let's go on this journey together and have fun today. Okay. So let's get started. Before we actually go into the content, I'd just like to give you a few notes about what we are going to do today. The first of which is that, as I was saying, I'm going to try to go a little bit for accessibility. I'm going to make things a little bit more simple than they actually are. So if you want the real content, like the original sources of the things, it's here. You have the references down below. So I'll give you some links at the end of the presentation where you can go to check it out if you want to know more, etc. just take a note, and then I'll give you a QR code, and you can scan the thing, and you can get the links. Now, another thing that's important is that we are going to have some sections today with different parts of how transformers work. At the end of each section, we'll have a pink box like this. And it's going to be something to remember, a takeaway. We're going to have a few of those. And what we're going to do is we're going to remember them. Okay? It's like the key points of the presentation. And we need to remember that to go back to them later on. So using them, at the end of the presentation, we're going to be able to build a nice summary. Okay? Good. Now, with all that, we're actually ready to get started. And one of the things that, well, I think it's important to start with is like with the real basics. What do LLMs do? What's the real purpose of large language models? Well, to get started, I'd say that they are just a system that tries to fill the gap. So, for example, if I give you this, what's the next word? No swiping. Exactly. And you could go on and on, right? Swipe or no swiping, blah, 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 blah. Yeah, that's how they work. They just literally write the next word every single time. Now, how does it really work? That's the whole topic that we're going to cover today. But that's the key point of how they work, okay? Now, the underlying architecture is something that we call a transformer. That's, of course, not like this one, right? It looks a little bit more like this, which you may have seen around if you are into AI. Don't worry, we'll make it simpler. But basically, what I want you to know for now is that that's, let's say, the original transformer architecture that was introduced in a paper in 2017, but it's not what I'm gonna talk about exactly. I'm gonna talk about a smaller portion of that. So there's no laser. Well, I'm gonna talk about this part, okay? Just this part. That's the architecture of GPT, which I think is perhaps very interesting for some of you. So that's the thing that we are gonna be talking. GPT. So again, how does it work? I put a word inside this thing, then it runs through the model many times. This gets repeated many times. We'll see how it works. And then we get a prediction. So for example, swiper, no, and then we put the no, and we get the swiping, and it works like that all the time. Okay, is that clear? Yes? Yeah, good, perfect. So, our friend the map is gonna guide us through the thing we are gonna do. First, we're gonna talk about tokenization. How does it work? How do we get tokens? What are they? We're gonna talk about embeddings after that, attention. We're gonna really dive deep into that, a lot of content. And then we're gonna go to feed-forward neural networks here. Language modeling, that we use for language modeling. We'll try to train a model, and we're going to see how inference. So a lot of things today with our friend Matt that's going to guide us through the thing. So yes, we're ready to start this journey today. So tokenization. How can we represent words? That's a great question, right? For example, if you have this sentence here, how could you represent that? Well, you could just take the Unicode encodings of the different characters, right? So that would be the Unicode encodings, A, L, D, I, space, etc., etc. That's a way to represent words, but perhaps it's not very efficient, right? Because you need one Unicode character for each single letter. What if I give you something that's a little bit better? I'll give you one idea. Maybe we can just assign numbers to different words. So for example, Aldi becomes 1, the 2, etc., etc. And that way, I'm sort of compressing information, right? I just need 8 numbers to represent the same thing. Important, I can repeat numbers. So with a small table, I can express sort of complex messages. This is the purpose of tokenization. This is what we do with text. And that's how transformers start. We take a text and we try to come up with a representation that looks like this. Many numbers that represents the things that are in that sentence. Now, how do we really assign the numbers, right? Because, well, here I just wrote 1, 2, 3, but how does it work? How do we train a tokenizer? Well, we can do it with a very simple algorithm. So, for example, what we can do is that we can start just assigning numbers to letters, just like before. So, for example, Aldi the blah, blah, blah becomes ALDI space here, you see? ALDI space, no. Okay, that's how we start, but now we start merging things. So for example, here we can see that we have TH 2 times. So maybe we can compress this thing. Maybe we can merge the 2 characters. So what we do is that we create a new entry here, and we just write 28 means TH. And we write a 28 here. We start repeating this process with a lot of texts. We take a lot of texts to learn how can we represent words. And we just repeat this process many times. So now we have compressed the word the into a single number. And if we do this thing many, many times, we just get something like this. This is the tokenizer of GPT-4o, and you can see that full words become one number. You see? One number, etc. So that's the first step to processing a text, tokenizing, getting the numbers of the words. Now, are we clear? Yes? Good. Now, tokens are encoded words. That's the first takeaway that we have here, okay? Let's remember this thing. Tokens are just numbers that represent words. So, first step done. Let's move to embeddings now. What are embeddings? Well, I would say that an embedding is sort of an idea. It's a concept, a representation of something. But how can we express an idea? I'll just do it with one example, perhaps. So, for example, I'll just represent supermarkets here, okay? Irish supermarkets. So we're going to have an axis here that is quality, and an axis here that is price, right? So, for example, if I give you Tesco, where is Tesco here? Where, more or less? Here? Here? Okay, I'll give you my answer. My answer. For me, it's sort of here, right? I mean, it's not the best, but it's sort of average. Now, what if I give you super value? What do you think about super value? More quality than Tesco, more quality than Tesco, more expensive, more expensive. Yeah, I agree. So maybe here, right? Yeah, okay. What about down stores? Quality? Yeah, a lot of quality, and mid quality, sort of. Okay, well, for me, it's a really good one, actually, right? I'd place it sort of here. Spar? What do we think about Spar? Oh, it's down. Okay. Yeah, it's also very, but it's on the pricey side of things, right? It's super pricey, but not that good. Yeah. And what about Lidl? Average, price average, quality here. Yeah. So, well, I placed it here, but that's perhaps because there's Aldi. Where's Aldi? Well, I'm going to give you the only real answer that you can give me here in this talk, which is that it's great and super cheap. That's the best supermarket. Now, why am I showing you this? Well, because what I'm representing here are ideas. This is the idea of being Aldi. Aldi means good quality, low price. What is Lidl here? Well, low price, not so much quality, etc., etc. And we can actually measure things. We can say, well, Lidl is in this position. It's this much quality, this much price, etc. We can give numbers to things, and this is the key idea of an embedding. We're going to use very simple embeddings here, just 2 dimensions, because it's easier to represent things. But in reality, language models, of course, have very big embeddings. So big that we can't really see them. You know, it's like 500 numbers, 1,000 numbers, things like that. So of course, you can't put them in a chart like this, but I hope you get the idea that an embedding, a list of numbers like this, is just something that you can represent and that gives you a meaning, sort of, right? There's an sort of like a intrinsic significance to an embedding. Now, of course, when we start using our models, things are not correctly placed, right? We just randomly initialize embeddings, and then we start working with our model. We move them around, and we get to something like this after training. But of course, embeddings are not magical. They start in random positions, and they need to be trained. Now, let's talk about how we actually get embeddings for words. That was just an example to sort of explain the idea of what's an embedding. Now, how do we get embeddings for tokens? So, as I was saying, of course, we have things in random positions at first. So, for example, swiper can be here. You know, we can have like different things in different positions, and they may not necessarily mean something specific. At first, they are just in random places. But I'll keep going with one example. We'll have a sort of running example throughout the presentation to explain how this sentence would get processed. Okay, so Aldi takes the comfy backpack. For example, that's a token that is just one word, but it gets broken down into 2 units. You remember we had the, and it had th and a separate e, right? So that's the same thing. Sometimes there's words that are not just one token, they get separate in just 2 different tokens. So that's one of the things that we can have. And of course, they have different numbers, right? That's tokens. Now we get the embeddings of those things. It's just a list. We go into the model, there's a sort of table. I look. Okay. What? This song, sorry. It's a swiper? Just swipe. Oh, here, right? Or swiper? It's not here. There's swiper. Okay. Oh my God. I need you to say swiper. No swiping. Swiper. No swiping. Swiper. No swiping. Oh, oh no, no. He's here already. Oh no, shit. Oh fuck. No. That's bad. He's messed up all our embeddings. Where are things? How can we get the original positions of things? Because you remember I told you embeddings are just one number, I look them up in a table, and I get the embedding. But do I have information about the position of each thing? Do I know if this goes first, or this goes first, or this goes first, just by looking at the number? No. Oh, that's a problem. That's a problem because, you know, how can I reconstruct the original information now? I can't. So that's a great question. How do we know the positions of the different embeddings? That's one of the problems that transformers need to solve, because if we process a sentence, it's really important to know where each word goes, right? It's not the same to say some sentences in one order us saying the same thing, but in a reverse order, for example. It's not the same thing. So how do we know the position? Well, what we do is that we add a sort of special signal. That's a little bit about mathematics, etc. But I'll just give you a simple idea here. Something that we can do, for example, is we can just write numbers like this next to the embeddings, and then we just, for example, add them to one of the coordinates. This is a simplified version, but you see what I did here? I added the number here. So now, if I have this, I'm able to reconstruct the order. So when the system gets to process the embeddings, it will know where each of the things was located. And that's really important to understand the meaning of something. So that's, let's say, my point about positions. Now let's forget about this thing because it gets like a little bit more complicated. So let's pretend like these positional encodings don't exist, okay? But this is something to be aware about. Position, it plays a very important role and it goes into the embeddings. So I hope that was clear, yes? Good. Okay, so takeaway. Embeddings represent ideas. They represent ideas. We started with tokens, we embed the tokens, and now we have ideas that we can process. Now, how do we process ideas? Well, that's where we start to talk about attention. So what's attention? This is a word that many people talk about, right? Perhaps you've heard about attention, I don't know, like in a podcast or YouTube, or maybe you've read some papers about attention. It's a very interesting topic. I'm going to try to make it very simple. First of all, why attention? Why do we need attention? So I'll give you just one example. We have our sentence here, right? Aldi takes the comfy backpack. Now, what happens if we have a different sentence, which is Aldi takes the secret back door? There's something here. We need a different prediction. And how do we know how we can make that prediction? If we just look at back, if we only have this context here, we have no idea. Right? We need more information from the different things in the sentence to influence this thing. Specifically, for example, we need to look at comfy, right? Comfy backpack makes more sense than secret backpack, right? Secret backdoor would be probably an answer there. So we need to sort of communicate the information of what's the context here to this token, so that we can make the prediction for the next token with the context that's around that thing. That's clear? Yeah? Yeah? Not so clear. Yeah? Yeah? If this is not clear, stop me. I can, explain things like a little bit more. I just want to be sure that we're on the same page, because now we're going to look at attention. So is it good? Yeah? Very good. Okay. So context matters, information needs to flow around. How can we do that? I'll give you an analogy first, and then we'll actually look at the thing. Just imagine we have a key that unlocks a lock. And once we unlock the lock, then we do something else. So for example, if I have comfy, I use this to unlock back. And then I do a change to back. For example, I add the concept of being soft. A backpack is soft, so I say to back, okay, you are soft. So on your prediction, you should take that into account and predict pack, you are a backpack, right? So we want to communicate this message to back only when we have comfy. We unlock the lock, and then we do the update. That's a little bit the idea here. We get like this sort of new representation. And that's how we make our prediction. Now, we're going to talk about three things here, the three elements, right? The first, the keys. The second is not going to be called a lock. It's going to be called a query, okay? Keys, queries. And the third thing, the update, it's going to be something that we call the value. The thing in red, it's the value, okay? Good. So how do we work to generate those keys that will unlock the queries later. Well, I'm gonna give you, so this is just for the sake of the example. It wouldn't work like this in real life, but for the sake of this example, let's say that this somehow encodes the type of word, for example, okay? So here we have back, it's a noun, so we have like 1.3 here. And it's a different type of word from takes, for example, it's a verb, so we have a different value here in this coordinate, okay? Yeah? Clear? Good. Now, the second thing is going to encode hardness. How hard is this thing? So, for example, a back door would probably be very hard, right? It's like solid. So that's one in principle. Now we're going to try to change it to make it softer to predict backpack. So first coordinate type of word, second coordinate softness. Good. So what we do here is that we have a key matrix. This is just a thing that's learned over time. The model learns this thing when it's trained. It's, you know, like GPT has been trained for like literally weeks with lots of examples just to learn things like these, like the key matrix. The key matrix encodes special information. And what we do is that, and I'm gonna ignore the rest of the tokens, I'm gonna focus on these two. What we do is that we just do a matrix multiplication. How does it look? It looks like this. I take this and I start multiplying and summing. So for example, we generate a vector here, a list of numbers that has 3 numbers. And those numbers are the answers to specific questions like these ones. Can you see the questions? Those are random things I thought about, but the key matrix can encode some meaning over time. It's like literally asking questions. It's saying, is this an adjective? Yes, it's an adjective because we have a 1 here and this matches the 1 here. So we write a 1 here. This is an adjective. Can I eat this thing? No, it doesn't match. Is this alive? No, it's not alive. It's like asking many questions, and we would have hundreds of those questions, literally hundreds, and we just get the answers to each of the questions. Of course, those questions are not simple like this, right? Like in real life, you would have hybrid questions, things that are not really easy to interpret, but the idea behind the whole thing is that we try to get some special representation of these tokens here to use them as a key for a next step. We do this with Comfy, and we do that with Backpack as well. Is this an adjective? No, it's not an adjective. Can I eat this thing? No, I can't. Is this live? No, it's not alive. Very good. So we have our keys here. Now, again, that's the answers to that. We need our queries. We need our lock now. How do we unlock this thing, right? We need to generate that thing as well. And it works the same way. The only change here is the matrix. Now it's going to be called a query matrix, and it has different values. So essentially, we're asking different questions because, for example, now we like just want to literally ask for different things. Sorry, that I forgot to change that. So questions like this: is this a noun? Is this hot? Is this in Asia? Anything you can think of, right? So we take, for example, Comfy, and we just do the same process. We just start answering the questions. Is this a noun? No, Comfy is not a noun. Is this hot? Not particularly. Is this in Asia? Doesn't really make sense to ask that, right? So that's what we do. Again, same process, but we do different questions. We do that with Comfy, and now we do that with Back as well. So is this a noun? Yes, it's a noun. Is this hot? Doesn't really make sense. Is this in Asia? Again, it doesn't make sense as a question, right? So 1, 0, 0. That's our query embeddings here. Is this clear? Yeah? Good. So now what we need to do is we need to combine them, right? We need to unlock the lock. So how do we do that? Here's the things that we had. We're gonna place them differently. And we are gonna combine them. So for example, here we can combine the key of Comfy with the log, the query of Comfy as well. And we're gonna do the same for the different elements here. So we ask here, how good are the different matches? We multiply here. Now, how many matches did we have? We sum here. So that's our value. That's our attention value. That's how much Comfy cares about Comfy. And we do that for the different things that we have here, and we get our attention matrix. Yes? Good? This is a key part of the presentation, so I hope this is clear. This is how much does Comfy care about Comfy, how much does Comfy care about back, how much does back care about Comfy. How should the information flow here? Yes? Good. Very good. So now we have our answers to the attention matrix, and we just have this encoding of how much does each thing care about other things. Of course, again, this is more complex. You know, there's many tokens, there's many layers in the system. So it gets really complicated. There's a lot of parameters here to learn, to process, etc. That's why models consume so much. But the key idea is just this thing of matching something to something else. Can be really confusing if you try to analyze that in real life. Now, there's the last part of the thing. Once we know that we want to get some information from something, right? We used our key to unlock the lock. Now, what exactly should we change? What's the update that we should make to one of the embeddings, right? That's the value, the change that we want to make. So that's something that we want to generate as well. If there's a match, how should I adjust this thing? And we just do it more or less in the same way. So you can see that here I have Comfy, and I say, well, if this is a movie, you should increase the degree of beauty, for example, of the movie. If this is a soft adjective, you should decrease, sorry, if this is a hard adjective, soft adjective, you should decrease the robustness of the back token. Okay, so this is the update that you want to perform. So again, we just do this thing. And what do we get here? This is especially important. You can see that we want to update back by a high degree. We want to change back a lot, right? So now that's when we come back to our attention matrix, which told us what updates do you need to make. And we also have our values, which tell us exactly what's the thing that I need to change if I should make this update. We just combine them in the same way, like it's literally all matrix products all the time. So we combine the two things again, and we get our updates here. You see, we generate our different values, and we have our updates. And now we just sum. We have our embedding here, and we sum this thing with the update that we want to make to this thing. Now, can you see this has become softer? This was the dimension that encoded the degree of hardness of the thing. It used to be like this. Now it's softer. So my backpack has become softer in a way. So this is how attention works a little bit. The key point here is that attention helps information flow from one place to another. And that's the key mechanism to be able to communicate parts of things. Now, we are here speaking about attention, but sometimes it's not just about communicating information. Sometimes there's something more, which is you really need to process what you have. You need to understand the meaning and change things based on the meaning. It's not just communicating different parts of the sentence. That's the goal of something that we call the feed-forward neural network. That's a part of the transformer as well, and it comes after attention. So let's say that now we have those things. After attention, we performed our attention mechanism, and we get something like this. You see back now has become softer, but we need to process that. Now, since there's no flow of information, or in other words, since everything is treated independently here, I'm only gonna talk about back here. I'm not gonna talk about other parts of the system or anything like that, because everything is done in parallel. So no flows of something to the other, so we can ignore the rest of the tokens. I'm only gonna talk about back, okay? Good. So we take our thing that is called a feed-forward neural network, and how does it work? It's the same thing all over again. But now we ask, again, different questions. Something like, for example, is back a pizza recipe? No, it's not a pizza recipe. Is back a Nobel Prize winner? No, it's not a Nobel Prize winner. Part of a computer? No. Soft noun? Oh yeah, it's a soft noun. Okay. So that's our answers to the different questions we were just asking a second ago. And now we have this embedding here. What do we do with that? We do an activation function, which is something very simple. For example, you can say, is this thing more than one? So we start looking here. No, 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 yes. That's our answer. That's the answering numbers. So we can get something like this. And if we have a representation of our answers to the different questions that we are asking, now we can take our answers and we can transform them into new embeddings that encode perhaps different things. So same process again. We have a feed-forward neural network again. It's part of the same one. We just communicate information, but now we reduce the size of the embeddings. You can see that here we have 4 dimensions, the answers to the different questions. Now we're going to go back to our 2 dimensions, which were the type of word and the level of hardness of something. So we put this thing here, and we get a new embedding. You see? It's changed a lot. Before, it was telling us, we have a noun about something that's neither soft nor hard, right? It's like 1.1 and 0. That meant we have a noun, and yeah, something is like not particularly hard or soft. Now, we process this thing through our feed-forward neural network, and we get a new embedding like this, which means, for example, I mean, I'm just coming up with examples here, right? But for example, it can say, this is a suffix that is about something soft. That makes sense. We want a pack, which is about a backpack that is soft. So that makes a lot of sense. We would, for example, get predictions like, nouns about something that's neither soft nor hard. Probably that's grass, coffee, bird, or things like that. Now we are actually looking for suffixes about something soft, which can be pack, inkle, twinkle, things like that, something soft, a suffix. Ish, that's something that you also put in, cute things that are small. So it could look like that. You can see the transformation happening right in front of your eyes here. Now, takeaway here, neural networks process the meanings. We communicate meanings first, and then we process those new meanings. Great, we are going full speed here. We just have to talk about one last part of the transformer architecture, which is, to be honest, I think the easiest part. So the hard part is sort of done. Now we just need to convert embeddings into words. I just told you some examples. I told you this is coffee, grass, blah, blah, but how do we actually get to that? How do we get the words? That's what we call the language modeling head. That's the last part of the transformer, this part here. So this part takes care of, I have those embeddings, and I'm going to give you a word. I'm going to give you an answer. how does it look? Well, we have this new embedding for back, and we can just literally start asking questions for specific words. So, for example, house, Aldi, the, etc., etc., etc. A lot of words, maybe thousands of words. This is a very big matrix that has all of the different token numbers that I learned at first. You remember we had the tokenizer that had different numbers and was learning the different things. You know, it said the means this number, etc. Now we ask that question for every single number. We ask, how much do you think this number would be the next word? And we get something like this. Now, the problem with that is that this is not what we call a probability distribution. A probability distribution is just something that has two properties, at least in this context. Things that we care about here is that everything is between 0 and 1. So that's not the case here because we have something that's not between 0 and 1, right? And everything sums to 1. Clearly, this doesn't sum to 1, right? It's probably a different number. So this is not a probability distribution. What do we do here? We literally just sort of squeeze things into that range. So we had those numbers here, you know, like something that's very low, high, etc. And we just get, with a function that's called softmax, if you're curious, numbers like this, 0.4, 0.5, 0.1, and now they are between 0 and 1, and they sum to 1. So this is a very nice property that allows us to say, oh, I think that the next word is 50% likely to be pack, and 40% likely to be door, things like that. That's the output of the model. Now, perhaps this is just a side note, but if you use LLMs, so for example, on the OpenAI API or things like that, you've probably seen something that's called the temperature, right? This is where the temperature goes. This is the part where you apply temperature. How do you apply temperature? What you do here is that you take this thing here, and before you normalize the thing, before you get your probability distribution, you just change this thing. For example, if you multiply by 5, what happens here? You get values that are much more extreme, right? For example, this one becomes minus 11.5, 15, 14, things that are way more extreme. And when you apply the softmax function, what you get is values like this. You remember we had a 0.5, 0.4. Now you get a probability distribution that's sort of much more confident in the answers that it's giving you. Because now it's telling me, oh, I think it's 80% pack and 20% door. You can do it this way, or you can do the opposite. You can also literally divide the numbers that you have here, and then you get less certainty. Now, the way I'm showing you the temperature here is not exactly the way that OpenAI shows it to you. OpenAI shows the opposite, so the inverse of this number. So here, OpenAI would show you a 0.2 temperature. You just divide by 1. 1 over 5 is 0.2. That's the temperature that OpenAI would use here. Does it make sense? Yeah? This is a very simple change, right? It doesn't really affect the model or anything like that. It just affects the way that you do your predictions. So, okay, well. Takeaway, language modeling turns ideas into words. And that's more or less the transformer architecture. That's the transformer architecture. Now we're going to have a little bit of a demo, sort of, about training a transformer. I'm just going to show you very briefly because, you know, I don't want to be boring or anything like that. I'm just going to show you a little experiment here that I coded. I don't know if it's going to work or not, but we're going to try to train a very simple transformer. Okay? And, well, I'm just going to run the thing because it takes a while, and then I'll take questions in the meanwhile. So here I just have literally a Jupyter notebook where I'm using subtitles from Dora the Explorer, the first season of Dora the Explorer, and I just load the subtitles, I process them. Here we can see a tokenizer that gets trained. I can explain the code if you want, but it takes a little bit of time. So if you want the explanation for the code, I'm happy to do it a little bit later. You know, like first I want to take like general questions, etc., and we can look at the code after if you want. So we just load the different subtitles, and first we train our tokenizers. That's the first part of the presentation. You remember we were telling the tokenizer, oh, you should learn associations between words. Well, that's what happens here. You see, for example, I have, oh my God, sorry. I'll just change the display settings. Sorry, I thought you were seeing my screen and you are not. Okay, can you see my screen now? Yes, it's working. Sorry. Okay, so we load some subtitles from Dora the Explorer, right? And then we just train a tokenizer. Literally the process we were seeing before. We have some different letters and we start making associations to create bigger tokens. So for example, here, Aldi the Explorer take me on an adventure gets turned into something I will explain in a second. And then Aldi the Explorer take me on an adventure. So we have this sort of phenomenon of some words that are just one token and some words that are not just one token. They get broken down into smaller things. Now, we can, well, define like classes for models, etc. Here I'm literally just defining the different components that we talked about: attention, the feed-forward neural network, how everything comes together into literally just one class. And I'm gonna leave this here. It's gonna train on the background, and I'll just explain to you in a second what's this thing that's called text start. You saw it here, right? Text start. Why do we have this thing? Do you have any ideas about that? Why do you think people put this thing that's called text start, which is a token? It's just one number. Why do you think we have that? Wait a second. Sorry. Yeah, I'm going to give you the mic here.
Like maybe because you need an input to predict the next one. So if it has nothing, it doesn't know what to predict. But if it has like the start token, at least it knows predict a common first word.
Yeah, that's the perfect answer, really. Very good, very good. That's the answer. So why do we have text start? Well, we were just, you know, like exploring transformers a little while ago. We had some words here, but since the task that we have is to always predict the next word, what happens if we want to predict the first word? What happens if I want to predict Aldi? I need something, sort of a dummy token. That means I start here. This is my start. Give me the first word. That's this one here. That's the text start token here. So very good answer. Now I'm ready to take more questions while we train the system here. Any questions? You have a few. We have some here. Oh, yeah. Thank you. Do you want my... I'll just give you mine.
Can you tell me about more about softmax, what it works and how it works? Like, I don't know about that.
Sorry, yeah. I sort of skipped over that, but let's go back to the presentation here.
It's working now.
Yeah, it's working. Good, good. So let me go back. So we were here, right? Yes. And we wanted to convert this into this thing. And that's where I said, oh, here we apply a thing that's called softmax. Softmax is just a function I mean, you can look the definition in Google, but it's literally the exponential of like so this value here, you exponentiate that to like literally whatever base that you choose, you exponentiate that, and you divide that by the sum of all of the exponentiated components. I know that's not very clear, right? That's sort of why I skipped over that because like, it's hard to explain that just with words. But basically the idea here is, so something that you could do here is come up with a function that somehow maps this thing into numbers that are between 0 and 1. And you could, for example, write an algorithm here, right? You could say, oh, if it's less than 0, you write 0. If it is, you have a problem here because what's the limit? You have no limit. That's a little bit hard to write an algorithm for. So that's where softmax can help you. You could also just literally divide by the sum of all of the values, and then you would get a normalized distribution. What's the nice thing about softmax is that it gives you sort of a smooth shape. So if you were to plot the values here, it has sort of a nicer smooth shape. I mean, here you don't really see it because we just have a few examples, but let's say when you're doing language modeling, what you get is a nicer distribution that's sort of more balanced when you use this function to normalize, which is called softmax. But it's not the only way that you can normalize. I hope that's sort of clear. I know it's hard to visualize probably.
How it decide like positive value should be 0.8 or 2.2.
So your question is, we have a lot of 0 values here, but how does this function decide if I should have a 0.8, a 0.2, etc.? That's just the mathematical properties of the function, of course, but I mean, what you can see here is that the highest value is 15, right? So I should give more weight to that. Here we have a 0.8. Then we have very low values, for example, minus 14.5. That's really low, so it should be as close to 0 as possible. If we had more precision here, we would probably have something like 0.0003. It's not 0.0 exactly. It's like a smoother shape, if that makes sense. Yep? Good. More questions? How do I handle out of vocabulary tokens? That's a great question. The answer is that you literally, so the tokenizer, when it doesn't know how to encode something, 2 things can happen. If it's just literal letters that you don't know, you can, like in the worst case scenario, you would just encode the letters. The letters are still a possibility as tokens. So, letter A is 1, letter B is 2, letter C is 3. So they would still be encodable as tokens. Now, the problem happens if you have something like an emoji. An emoji sometimes, it's like a different Unicode encoding. Sometimes the tokenizer doesn't recognize that. So for that thing, what you do is that you have a special token, which is called the unknown token, which maybe I have here. Just give me a second. You see, this is what you do. Oh my God, sorry. sorry. So what you do is that you just put your unknown token, which I'll show you in a second. Here it is. You see? That's the unknown token. It's a special ID that just means I don't know how to encode this thing, so I'm just going to give you this number because I don't know how to write this thing. That's what you do when you don't know how to encode something. More questions? Or we can, yeah.
Just have a question on the temperature. How does that affect model output? You said it just increases the sensitivity, right? In a sense, how correct the response of the model would be. So shouldn't that be like defined within the model itself? Like ideally, you would want as correct the answer to be?
So that's a very good question as well. So what happens here is that yeah, we need to power on the thing. Okay, here it is again. So what happens here is that when we get the outputs of the model, this is where we were applying the temperature, right? So here I was saying I apply a temperature of 0.5, which means 0.2, which means you multiply by 5. And here we get more extreme values. People say this is like reducing the creativity of the model because you're literally telling the model, whatever you give me, make it 5 times more certain. Like it's like you are 5 times more sure about your predictions when you give me the answer. You multiply everything by 5. Now, if you increase the temperature, what happens here is that you divide the numbers. So for example, if you give me a temperature of 2, I would divide things by 2 here. So the numbers would become much smaller, right? They would be smaller numbers, which means that I will get a probability distribution at the end here that looks smoother. I would have, for example, maybe this would be a 0.3, and this a 0.4, and this a 0.2. You know, like it would be less certain about things. So that means it's more creative, because now it's probably gonna give you more bullshit, probably, but it's gonna be choosing more uncommon things when you increase the temperature. Does it make sense?
It will make the predictions of the model more certain or uncertain if you increase the temperature, sorry.
So it depends. So if you increase the temperature, the predictions of the model are less certain. And what I mean by less certain is that you would get more numbers here that are 0.1, 0.2. This wouldn't be 0.8. This would be 0.3, 0.4, lower numbers. So the model is less certain in what the model is giving you. That's if you increase the temperature. If you decrease the temperature, what happens is that this happens. You get predictions that are like, oh, I'm 80% sure that this is the answer. Yes? Yep.
Okay. Yeah. So for a specific temperature value, right? If a model is given an input, the lower the temperature, more chances are the response of the model will be same or closer to what it will probably predict every time. And higher it is, it'll just probably be it could be best at like random as well.
Yeah. So just think about this. For example, what happens if I choose a temperature which is 0.0000, something very small, something super small. You can choose 0 because if you, here I'm multiplying, but what OpenAI does is dividing. So if I divide by 0, that is not possible. So just imagine I choose 0.0000, something super small. What you would see here is that this number would be 1.0 almost, and all of the other things would be 0. So it's like saying you need 100% to choose this thing. So it's sort of deterministic in a way, right? It's forcing you to choose this token here. It would be 1.0. So it's like, yeah, this is the answer 100%. But just a comment here, perhaps, LLMs are not like necessarily random. Like you can see here that everything we did is just multiplying things. And if I repeated the process, I should get the same things. The part where we have sort of randomness is that we put a thing that's a random seed here. So here, now if I start writing more words, I would need to make a choice, which is, do I choose this word? Do I choose pag? Or do I choose, for example, this one? Do I choose door? Which one do I write? And I make that decision. That's what, for example, ChatGPT does. Sometimes it chooses the first option, sometimes it chooses the second option, and that's why it looks random. That's why if you press the regenerate answer, you get a different output, but it's just because it's making different decisions. And if I make different decisions, the next predictions will also become different. So that's why it looks random, but it's not fully random. Now I'm gonna change my screen again, and we can perhaps take a look at the generations of the model. Here we are, tokenizers. We defined the model here. That's a lot of code, I know. But what we care about is that I'm just gonna ask the model a very simple question. What do you write if I tell you, do you see? And what did it generate? Do you see the lake? Where, yeah, there's the ice cream truck is. Come on, thanks. Okay, maybe. It's not perfect. I can try other things. Give me another sentence. Let's try another sentence. Something you can, so just keep in mind that this is trained with Dora the Explorer. So it doesn't know how to write about science or anything like that, right? But if you give me perhaps like another start of a sentence. Sorry, what? Swiper. Yeah, swiper. Let's write swiper here. Swiper. And we just generate text here, right? Swiper, no swiping. Oh man, thanks for helping us stop Swiper the fox. Swiper, no, blah, blah, blah. So, well, it looks like it's learned a little bit, right? Of course, you wouldn't expect this model that I just trained in 5 minutes to be perfect or anything like that, but that's how you do training. When you actually train GPT, of course, it takes weeks and you need a super huge cluster for computing things, but that's a little bit about how you can train the models. And if you want, I can guide you through the code, but I think that's a very long thing to do. So I'll try to go for some conclusions here. And then if you want, you can come to me and we look at the code together here if you're interested. Sorry, let me go next. Yeah, so training is very expensive. That's my takeaway for what's about training, right? It's very expensive. Inference, my takeaway is that it can be imperfect. Many times, it's not very good, but sometimes it works. I'd say it was decent today. And that's our journey today. We've taken, well, a lot of steps. We talked about a lot of concepts today. Let's recap. We did it. So what did we do today? We learned that tokens are numbers. And those numbers represent items, right? It's a big dimension. What do we do with that? We communicate patterns. Attention makes things easier to bear unique experience. With that, you can use new process to get new things and we just do language which take those things and it executes. Of course, we saw an example of training, which is I just did it on a very small data set here. It's very simple, but GPT takes a lot of resources. Expensive. Inference can be perfect, but that doesn't happen. Thanks. That's it. The talk today. Thank you. Now, my last task, if you just appreciated the Dora the Explorer thing a little bit, or maybe you hated the idea, just tell me here. What did you think? What was your favorite part today? Did you like it? Did not like it? You don't need to answer questions. There's some questions where you can write words. You don't need to do that. If you want, it just takes like 20 seconds. It's like 1 to 5. 2 questions, super simple. And if you can help me with that, I really appreciate it. Because, I have like a lot of fun doing this, but I don't know if you had as much fun as I did. So that's why I really want to, get some feedback, improve things, and see how it goes. Perhaps as an incentive to you, all of the materials are in the form after you fill in the code. Does the form work? No, it's not working. Is it working, the form? Okay, I'll just give you a new code here because maybe I did something wrong. I'll just give you a new code. Just give me 5 seconds. Well, I'll give you the QR code now. But really, I just wanted to say that I'm really I'm really happy to like having able to try this new presentation. It was a new concept. I've never ever done it ever before. So I hope you enjoyed it, and really happy to have had you today. Are you sure it's not working? Good, good, good. Yeah, yeah. Very good. I'll just let you perhaps try again, maybe, because I have some answers here. So is it working now? Good, very good. Okay, thank you very much. Now I'm here for questions. If you want to look at the code, I'm here, but I know that's perhaps too much for some of you. So just come to me. We look together at this thing, and we have a little bit of time now to, just grab some food, some water, etc. Thank you very much.